In probability theory and statistics, the geometric distribution is either of two discrete probability distributions, the probability distribution of the number X of Bernoulli trials needed to get one success, supported on the zeta A1, A2, A3, A. The probability distribution of the number Y equals a zeta A1 of failures before the first success, supported on the zeta A0, A1, A2, A3, A. Which of these one calls the geometric distribution is a matter of convention and convenience. These two different geometric distributions should not be confused with each other. Often, the name-shifted geometric distribution is adopted for the former one. However, to avoid ambiguity, it is considered wise to indicate which is intended, by mentioning the support explicitly. Unregistered trademark S. The probability that the first occurrence of success requires k number of independent trials, each with success probability p. If the probability of success on each trial is p, then the probability that the kth trial is the first success is. For k equals 1, 2, 3, the above form of geometric distribution is used for modeling the number of trials until the first success. By contrast, the following form of geometric distribution is used for modeling number of failures until the first success. For chi equals A0, A1, A2, A3, A. In either case, the sequence of probabilities is a geometric sequence. For example, suppose an ordinary die is thrown repeatedly until the first time a 1 appears. The probability distribution of the number of times it is thrown is supported on the infinite set A1, A2, A3, A. And is a geometric distribution with par equals A1/6. Moments and cumulants. The expected value of a geometrically distributed random variable x is 1/p and the variance is p2. Similarly, the expected value of the geometrically distributed random variable y equals zeta A1 is qp equals/p, and its variance is p2. Let I1/4 equals/p be the expected value of y. Then the cumulants of the probability distribution of y satisfy the recursion. Outline of proof, that the expected value is p can be shown in the following way. Let y be as above. Then, the interchange of summation and differentiation is justified by the fact that convergent power series converge uniformly on compact subsets of the set of points where they converge. Parameter estimation. For both variants of the geometric distribution, the parameter p can be estimated by equating the expected value with a sample mean. This is the method of moments, which in this case happens to yield maximum likelihood estimates of p. Specifically, for the first variant let chi equals ak1, a. A kn be a sample where Kia permil beta 1 for ia equals a1, a. An. Then p can be estimated as. In Bayesian inference, the beta distribution is the conjugate prior distribution for the parameter p. If this parameter is given a beta, I plus or minus, ai squared prior, then the posterior distribution is. The posterior mean e, p, approaches the maximum likelihood estimate as I plus or minus and I squared approach 0. In the alternative case, let k1, a. A kn be a sample where Kia permil beta 0 for ia equals a1, a. An. Then p can be estimated as. The posterior distribution of p given a beta, I plus or minus, ai squared prior is. Again the posterior mean e, p, approaches the maximum likelihood estimate as I plus or minus and I squared approach 0. Other properties, the probability generating functions of x and y are, respectively. Like its continuous analog, the geometric distribution is memoryless. That means that if you intend to repeat an experiment until the first success, then, given that the first success has not yet occurred, the conditional probability distribution of the number of additional trials does not depend on how many failures have been observed. The die one throws or the coin one tosses does not have a memory of these failures. The geometric distribution is the only memoryless discrete distribution. Among all discrete probability distributions supported on 1, A2, A3, A. With given expected value I1/4, The geometric distribution X with parameter par equals A1/I1/4 is the one with the largest entropy. The geometric distribution of the number y of failures before the first success is infinitely divisible, that is, for any positive integer n, there exist independent identically distributed random variables y1, a, and in whose sum has the same distribution that y has. These will not be geometrically distributed unless now equals a1. They follow a negative binomial distribution. The decimal digits of the geometrically distributed random variable y are a sequence of independent random variables. For example, the hundredth digit d has this probability distribution, where qa equals a1 and similarly for the other digits, and, more generally, similarly for numeral systems with other bases than 10. When the base is 2, this shows that a geometrically distributed random variable can be written as a sum of independent random variables whose probability distributions are indecomposable. Golomb coding is the optimal prefix code for the geometric discrete distribution. Recurrence relation. Related distributions. The geometric distribution y is a special case of the negative binomial distribution, with y equals a1. More generally, if y1, a are independent geometrically distributed variables with parameter of p, then the sum follows a negative binomial distribution with parameters ra and a p. If y1, a are independent geometrically distributed variables, then their minimum is also geometrically distributed, with parameter, suppose 0 a ra 1, and for chi equals a1, a2, a3, a. The random variable xk is a Poisson distribution with expected value ra kk. Then has a geometric distribution taking values in the set 0, a1, a2, a, with expected value /1 aar. The exponential distribution is the continuous analog of the geometric distribution. If x is an exponentially distributed random variable with parameter li, then where is the floor function is a geometrically distributed random variable with parameter par equals a1 aaa and taking values in the zeta 0, a1, a2, a. This can be used to generate geometrically distributed pseudorandom numbers by first generating exponentially distributed pseudorandom numbers from a uniform pseudorandom number generator, then as geometrically distributed with parameter, if as uniformly distributed in 0, 1. If and then we get an asymptotic exponential distribution with parameter of, since, see also, hypergeometric distribution, coupon collectors problem, references. External links, Geometric Distribution at planetmath.org. Geometric Distribution on MathWorld. Online Geometric Distribution Calculator, online calculator of geometric distribution.